Okay, let me take up architectural level approaches under static supply voltage scaling, and in that also let me talk of pipelining in order to have lesser power reduction and at the same time less area overhead. In the earlier lecture we talked of parallelism, in which we have used two copies of the actual circuit, because of which we have a higher reduction in power dissipation, which accounts for 0.277 of that of the P reference power. And the same parallelism can be considered by using some n number of copies, and whenever you are going to use more number of copies, that is greater than 2, you can call that the parallelism as multi-core parallelism. Therefore, let me talk of this multi-core parallelism in order to have power reduction. And here in this multi-core also I have taken 4 copies. We can go with any number of copies. Fine. Therefore, as the actual frequency is considered as 200 megahertz, if you are going to talk of 4 replicas, then you are going to divide the frequency with 4, so that a 50 megahertz frequency is going to use to trigger the latches. And of course, whatever the circuit you are going to have, that circuit is going to be replicated some n number of times, and here 4 number of times it has been replicated. And of course, we will be using 200 megahertz frequency in order to trigger this multiplexer in order to get the outputs of 4 multiplier cores or adder cores, whatever it may be. Fine. And that's how we are able to achieve lesser power reduction, but at the same time we are able to get same throughput. Even though the frequency is reduced, there may be increase in delay, but at the same time we are able to maintain a same throughput. Fine. And here let me show you some statistics. If the number of cores are 1 and if the clock frequency is 200 megahertz, and if we haven't gone for any voltage scaling, and that is why the total power consumption is 50. Of course, it can be any units, generally in the range of microwatts. And if you are going to replicate this one, fine, therefore you can use a frequency of 100 megahertz. The frequency is going to be reduced by 2, and the supply voltage can be taken less than 5 volts, that is 3.6 volts. And for these conditions, the total power consumption is said to be 8.94, a much reduction in power dissipation if the frequency is reduced by half and the supply voltage has been reduced to some lower value. And if the number of cores are said to be 4 and the frequency is going to be 200 divided by 4, it's going to be 50 megahertz. And the core supply voltage can be even reduced to a lower value, and here it is taken as 2.7 volts, and the total power consumption is 5.2. Similarly, if we take 8 cores, 8 copies, the frequency can be 200 by 8, it's going to be 25. Therefore, the supply voltage can be even further reduced to 2.1 volts, so that we are able to get a power reduction up to 4.5. Therefore, higher the number of cores, the lower the power dissipation we are able to get. And this is all about parallelism. And though you are going to achieve lesser power dissipation in case of parallelism, but there is a limitation with respect to this parallelism, and that is area overhead. Fine, we are going to achieve this lesser power dissipation at the cost of area. Therefore, in order to overcome this limitation, we are going to consider one more architectural level approach, which is nothing but pipeline. Now let me consider pipelining topic under this architectural level approaches. Okay. And according to microprocessor subject, pipelining is nothing but while executing the current instruction, at the same time if you are able to fetch the next instruction, so that if the execution of current instruction is completed, then immediately we can start the execution of next instruction, because it has already been fetched. And that's how we are able to reduce the amount of time in order to work with any process. And here also we are going for the pipelining in such a way that to reduce the area overhead in case of parallelism, but at the same time we are able to get lower power dissipation. Here I am going to consider the same example, that is 16-bit adder, And this 16-bit adder, instead of taking them as the replicas, instead you are going to split that 16-bit adder into two 8-bit adders. Fine. You can check that here, two 8-bit adders. And therefore the first 8 bits, that is A0 through 7 and B0 through 7, will be applied as the inputs to the first adder, and the output of this adder is going to be again 8 bits, and that is represented with some 0 through 7 bits, and that is going to be stored in a latch. And a carry is going to be generated from this adder. This carry is going to be applied as one carry input for the second 8-bit adder. And for the second 8-bit adder, the inputs are applied as the A bits 8 through 15 and the B bits 8 through 15. Fine. And these are directly applied to this 8-bit adder. And the resultant 8-bit output is going to be stored in the latch. And finally, these two are taken as the sum of some 0 through 15 bits. And finally, a carry is going to be generated from this 8-bit adder. Therefore, we are going to get a total of some 17 bits. Now, as we have splitted the 16-bit adder into two 8-bit adders, there won't be much area overhead. Fine. Therefore, with respect to these extra latches and some extra connections, there will be some 0.15 times the area incremental value. Fine. Therefore, the area overhead is said to be simply 0.15 times. Therefore, the area will increase by 1.15 times. As the area increases by 1.15 times, even the capacitance increases by 1.15 times. Now, let me talk of the frequency with which the inputs have to be applied to these adders. In case of parallelism, as we have considered 16 bits and we have considered a delay of 10 nanoseconds, because of which the frequency with which the latches have to be triggered is 100 megahertz. Fine. Now the total 16 bits have been splitted into two 8 bits. Therefore, at the maximum, if you are able to get a delay, means it's going to be around 5 nanoseconds. If at all, if you are going to have 5 nanoseconds, the frequency with which we can trigger the latches is going to be 200 megahertz. Fine. 1 by 5 nanoseconds, which is going to give out your 100 nanoseconds. Fine. Therefore, here what we are going to do is, in case of pipelining, instead of triggering the latches which are going to apply the inputs to your 8-bit adder at 200 megahertz, rather we are going to trigger them at 100 megahertz frequency. That means we have reduced the frequency by 2. Even then, you are able to apply a frequency of 100 megahertz. Therefore, as the frequency has been reduced by half, then definitely we are able to achieve a lesser power dissipation. At the same time, as we have reduced the frequency, simultaneously we can reduce the supply voltage also. Fine. Let me tell you what sort of or how much amount of power consumption that is going to exist without VDD scaling and with a VDD scaling. I repeat again, instead of reducing the clock frequency, the delay through the critical path of the functional unit is reduced such that the supply voltage can be reduced to minimize the power. Therefore, 8-bit addition is performed in each stage, and the critical path delay is going to be half that of the 16-bit adder stage. Fine. Therefore, we can reduce the supply voltage to a V reference by 2, but still we can operate the adder at 100 megahertz. Actually, for that 5 nanoseconds delay, it has to be operated at 200 megahertz, but rather we have considered this in 100 megahertz. Fine. Therefore, the capacitance has been increased by 1.15 times. Why? Because the area has been increased by 1.15 times. Now, let me calculate the power dissipation without VDD scaling. Therefore, the general formula for power dissipation is CV square F. Therefore, here without VDD scaling, of course, as the 16-bit adder has been splitted, though you haven't reduced the voltage, but the area has been increased, because of which the capacitance is 1.15 C reference. And of course, we haven't gone for any voltage scaling. Therefore, directly we are going to take it as V reference square. But normally without scaling, what is the frequency we need to apply? It has to be 200 megahertz. Therefore, it has to be twice that of the F reference. And that's why I wrote it as 2 into F. Therefore, without VDD scaling, how much amount of power dissipation is going to be there is, it's going to be 2.3 times that of the P reference value. Fine. Now let me talk of VDD scaling, and let me talk of how much amount of power is dissipated because of VDD scaling. Therefore the same formula, CV square F, but instead we have gone for pipelining. Therefore, the capacitance increases 1.15 times that of C reference. Of course, we can reduce the frequency. Fine. Why? Because instead of operating the circuit at 200 megahertz, we have operated that at 100 megahertz. As the frequency is reduced, definitely voltage is going to be reduced. Therefore, your voltage is going to be considered as half that of the reference value. Therefore, V reference by 2 whole square into EF. Fine. Therefore, the frequency with which the inputs are going to be applied is said to be the same. Therefore, your circuit won't be delayed. Therefore, the amount of power consumed is 0.28 times that of P reference. Fine. Therefore, which is going to be similar to the amount of power that is consumed in case of parallelism. But what is the advantage we are going to get with respect to pipelining is, here the operating frequency is F only. We are not going for F reference by 2. Fine. Therefore, your circuit seems to be faster when compared to parallelism. Now let me talk of impact of pipelining on area, power and throughput. Therefore, what about area without VDD scaling? Fine. Let me tell you the contents of this table. And in the first column we have parameter, and the second column the parameter value without VDD scaling, and in the third column the parameter value with VDD scaling. Let me talk of the area. Here we are talking of parallelism in both the second and third columns, but instead in first one we don't have VDD scaling, and in the second one we have VDD scaling. Therefore, area is said to be 1.15 times increases. Therefore, here also 1.15 times. And the power is, previously we have calculated, it is 2.3 times that of the P reference. And with VDD scaling, we are going to get a power of 0.28 times that of the P reference, which is said to be drastically reduced. Fine. And the throughput, it's going to be 2 times. And normally this has to be operated at 2F. But instead this is operated at F, and that's why the throughput is said to be 1 time. Fine. But we are able to maintain the same number of operations per given time. Therefore, your pipelining is said to be better when compared to parallelism. Fine. Therefore, we have some sort of power reduction in case of parallelism, and at the same time some amount of power reduction in pipelining. Now what happens if you are going to combine both parallelism and pipelining, whether we are able to achieve much lesser power reduction or not? Therefore, let me take up architectural level approaches where we will be going for a combination of both parallelism and pipelining. Fine. And as we are going to have parallelism, definitely we need to have multiple copies of the hardware, because of which here I have considered 2 copies of the same 16-bit adder. But again, each 16-bit adder is going to be considered under pipelining architecture. Therefore, each 16-bit adder has been split into 2 8-bit adders. Fine. Therefore, here we have area increase of 2 times, and at the same time extra interconnections and extra latches, and because of which it's going to be some 0.25 incremental value with respect to each 16-bit adder. That's why counting for 2 16-bit adders, it's going to be 0.5 times with respect to extra latches and interconnections. Therefore, the total area increase is said to be 2.5 times. Fine. And here the frequency, as we have used parallelism, definitely the frequency has to be reduced by half. Why? Because I have used 2 copies. But if you are going to use multiple copies or 4 copies, then definitely the frequency has to be considered as F reference by 4. Here, as I have considered 2 copies, here the frequency is going to be taken as f reference by 2. And of course, in order to collect the outputs from 2 16-bit adders, your multiplexer has to be operated at f reference frequency only. Therefore, let me calculate the amount of power dissipation with this VDD scaling and without VDD scaling in combination of both parallelism and pipelining. Therefore, this is without VDD scaling. Therefore, the area has been increased by 2.5 times. Therefore, even the capacitance increases by 2.5 times. Fine. And here, as we are going to reduce the frequency, and of course, we can reduce the voltage, but here we are not going to go for any voltage reduction. Why? Because here I am talking of without VDD scaling. Therefore, your V reference is going to be V reference. As we have introduced pipelining, definitely the operating frequency is said to be twice that of F reference frequency. Therefore, it's going to count for 5 times that of the P reference. Therefore, which is said to be a lot or a very large value. Fine. Now, let me talk of the combination of both parallelism and pipelining. The formula is CV square F again. Capacitance is increased by 2.5 times and frequency is reduced by half. Why? Because we are introducing parallelism here. Fine. And as we have reduced the frequency, definitely the voltage can be reduced, and you can decrease the voltage to a much larger extent. Why? Because within parallelism we have incorporated pipelining as well, because of which instead of reducing the voltage to 0.5 V reference, even we can further increase the voltage to a value lesser than 0.5 V reference. Therefore, here we have considered it as 0.3 V reference. Therefore, if the voltage is scaled by 0.3 V reference, the amount of power dissipation is said to be 0.11 times that of the P reference, which is said to be a very large reduction. Therefore, combining both parallelism and pipelining, we are able to get much more power reduction, but that is going to be at the cost of area overhead. Fine. Why? Because the area is going to be increased by 2.5 times, and if it is going to be 4 core, it may be around 5 value. Fine. Let me talk of the effect of scaling on these parameters. If area increases by 2.5 times, and even with VDD scaling also area increases by 2.5 times, and power means here it is 5 times, and in case of combination of both parallelism and pipelining, it is 0.11 times, and the throughput is, it's going to be 4 times. Why? Because we have introduced parallelism as well as pipelining, and here we haven't gone for any scaling. If you will be just going with 2F, fine, and we have again pipelining, and here it's going to be 1 time. Fine. Therefore, of all the 3 architectural approaches, fine, your pipelining is said to be the better one. Why? Because it's going to provide much lesser power reduction. At the same time, it's going to provide a reasonable value for the area. But the combination of both parallelism and pipelining will give much more power reduction, but it's going to be at the cost of area overhead. Fine. And of course, parallelism, it's going to provide much larger delay. Fine. That's why, according to my opinion, the pipelining is said to be the better option. And that's all about this architectural level approaches.